So in question number 4, we're going to try to kind of create our own recursive definition. Now that you've seen what a recursive definition is all about, we're going to try to use what we know to create one given a fresh table. So in number 4, it's telling us that the equation or the sequence in the table is arithmetic, but they're not giving us all the information we need. And usually, to be able to understand any sort of equation, recursive or otherwise, it helps to have all the information from the table that we need to know, like the initial value, the pattern, or the adder, etc. So let's think about this table for a second. I see that I go from 3 to something to 13, and then from something to 23. So the first thing you might want to do is ask yourself, well, what does that pattern appear to be? Well, I know that it takes me 10 numbers to get from 3 to 13. So if you figure there's a halfway point here, maybe that means add 5 and add 5. Let's see. 3 plus 5 would be 8. 8 plus 5 would be 13. Yep, it looks like that works. So let's see if we can keep adding 5 and see if that completes the pattern. 13 plus 5 would be 18. 18 plus 5 would be 23. Yep, it looks like we found the pattern. The pattern appears to be adding 5. So if I quickly go through the rest of these, I have 23 plus 5 would be 28. 28 plus 5 would be 33. So it looks like the pattern holds up. And then if I go backwards, this is the one part that's a little bit tricky, I would have to say something plus 5 that gives me 3 as an answer. And if you don't know what to do with that, or if you can't really think about that, then you can go backwards by subtracting 5 and figuring -2 would work. Either because 3 minus 5 is -2, or because -2 plus 5 is 3. So there's my table. I know the pattern is adding 5, and now I know all of the terms in it. So in question letter A, it says write an equation in terms of n that allows you to find the value of any term t of n. That's just a fancy way of saying write what we call an explicit equation. An explicit equation is what we've been calling just an arithmetic equation. And if you forgot what to do to write an arithmetic equation, it may be helpful to go back to your notes. You probably have some notes. Your notes may be on a separate sheet of paper. Your notes may be somewhere on the front side of the paper if you printed the packet like we kind of used to do in class. But we've been writing explicit or arithmetic equations for a long time, and we know there's kind of a formula to them. The formula for an arithmetic equation is to write t of n equals the initial value plus the adder times n. Now it could be minus if the adder is subtracting, so I'll just put plus or minus there as a reminder. Now let's think about this pattern. We know that initially the 0 term in the table is -2 and that it's adding by 5. So I can write this equation as t of n equals the initial value, -2, plus, because we're adding, 5n. Same as always, nothing crazy there. We know that's generally going to fit everything that we already know about arithmetic sequences. But in the rest of the question, it says, well, what does n stand for? Sometimes we don't think about that very much. But the table makes it a little bit more obvious to think about. When I look at my table, n is always whatever term number I want to look at. If I want to look at the first term, I look at n as 1. If I want to look at the second term, I look at n as 2. The fourth term, n is 4. So n just stands for the term number that you want to look at. T of n is the actual term itself. So if I said what's the fourth term in the sequence, that tells me to go to term number 4, but the actual fourth term in the sequence is 18. So t of n is the actual term in the sequence, or the actual value of that term. So n tells you where to go, but t of n tells you what it is. And that's kind of an important distinction, just so you know. Now in letter B it says, okay, well what if you had t of n plus 1? What does that represent? Well, we've seen that before. T of n plus 1 was what we saw in the recursive definition that I highlighted in number 3. T of n plus 1 is the next term. So if n is kind of like saying, hey, where are you right now? N plus 1 is saying, well, where are you going next? Like if you're at 4, n is 4, n plus 1 is 5. So t of n plus 1 is just saying, hey, what's the next term? You've told me where you are currently. You're at the 4th term. You're 18. But where are you going next? So t of n plus 1 represents the next term. It's almost like saying t of n is where you are now, and t of n plus 1 is where you're going next. That's usually what I like to think about. T of n is where you are now, and t of n plus 1 is where you're going next. So in letter C it says, write an equation for t of n plus 1, given what you know about t of n. I have an example to follow, because I have number 3, what I highlighted in yellow, so I'm going to follow that example. I'm just going to use it for this particular pattern. T of n plus 1 equals, I'm kind of copying this, to get to the next term, I take my current term, t of n, but I don't want to copy the plus 6, because remember the plus 6 was for this table. This table was adding by 6. I don't want to copy that into this pattern, because that's not what this table is doing. So let's adjust. Remember, to get to the next term in this table, we were adding 5. So I would say, again, t of n plus 1, to get to the next term, we take our current term, t of n, and we add 5. So notice how I adjusted the equation a little bit to fix the new pattern. This new pattern was adding by 5, so I adjusted my equation accordingly. Make sure that idea makes sense. Make sure that you understand why you would write the equation the way we did, given the example that we have, and the idea of the next and the current thing, just like we did in number 3. In the next video, we're going to look at some recursive definitions, some recursive equations, and we're going to make sure that they make sense with yet another new table.